Hey everyone, today we are going to cover definite integrals. If you don't have your calculator out, this would be a good time to pause the video and go ahead and get your calculators. All right, so example one says find the area under the function f of x equals 1 plus x over 2 from x equals 2 to x equals 6. Note, under the function means between the x-axis and between the function and the x-axis. All right, getting ahead of myself there. So let's draw out what I mean when I say let's find the area under the curve. So we have this curve, which is ry equals 1 plus x over 2. That's this red curve right here. And we say from 2 to 6. So we want to go up to the curve at 2, go up to the curve at 6. So we want to find from 2 to 6 between the function, which is that red line, and the x-axis. So this line right here. So we want to find this little triangle on top of a rectangle, really. So I'm going to shade in the whole thing. Use yellow first. We want to find this area. Well, let's use shapes that we've used in the past. So maybe a triangle and a rectangle. Okay. And I'm going to shade that rectangle into another color just so we can see the difference in the two. All right. So we want to find the area of the two, and I'm sure you're probably like, Katie, what are we doing? How does this relate to definite integrals? I promise we'll get there, so just hang on for a little bit. So our area is equal to the area of the triangle plus the area of the rectangle. And so the area of, and I hope you guys are enjoying the thunderstorm in the background, the area of the triangle is 1/2 base times height. So my base is 1, 2, 3, 4. My height of my triangle is 1, 2. So that's the area of my triangle plus the area of my rectangle. It's just base times height. So my base is 1, 2, 3, 4. So 4 times 1, 2. All right. So that is my area of this triangle sitting on top of a rectangle. And I'm going to calculate this out. Handy dandy calculator. By the end of the semester, you will probably be saying, hey, I'm going to use my handy dandy calculator. So I have 1/2 times my base times my height plus 4, and that was for my triangle, plus the area of my rectangle, which was just 4 times 2. Enter, and we get 12. So the area of this entire shape, not sure what you want to call it, is 12. Okay, so that's nice. How does that relate to calculus? So I'm going to have you do something real quick. I want you to find the antiderivative of 1 plus x over 2 dx. So we're going to find the antiderivative. And we get x plus x squared over 4. Okay, so now we're going to call this, because it's our antiderivative, we're going to call this our capital F of x. And now I want you to evaluate f of x at 6 and subtract it from f of x, or f at 2. I know, pretty bizarre, but this is what we're going to do. So go ahead and pause the video and do that. Okay. So our function evaluated at 6, our capital F evaluated at 6, is 6 minus 6 squared over 4. And then minus our capital F of x evaluated at 2. And we get 2 plus 2 squared over 4. And so what I get from here is 6 plus 9 minus 2 plus 1. And I'm going to just type that into my handy dandy calculator. 6 plus 9. I could have done that before. Minus 2 plus 1. And I get 12. Hey, that's pretty interesting. If I plug in my biggest number, my 6 here, that was my stopping point, minus my antiderivative evaluated at my starting point, I get the area. I get 12, which was what my area was. Yes. And so how we would do this in calculus, and I'm going to kind of scroll off to the side right under our picture here, and I'm going to write this formally now. Our area is equal to the integral from 2 to 6. So those are my bounds, what we call bounds. We start at 2 and we go to 6 of our function. So 1 plus x over 2 dx. And we're going to write this up formally. So I'm going to find my antiderivative. We're not going to worry about the bounds right now. And we get x plus x squared over 4. That's my antiderivative, but now I'm saying my area equals this. I really need to include my bounds somewhere. So I'm going to draw a straight line at the end and say evaluated from 2 to 6. So my bounds come down behind a straight line. So I'm going to say I'm taking this function and I'm going to evaluate at 6 and 2. So then we're going to plug in our biggest number. So that equals 6 plus 6 squared over 4 minus the function, our antiderivative evaluated at our lower number, which is 2 plus 2 squared over 4. And we can type this into the calculator straight like this, which I find a little bit easier. So open parenthesis, 6 plus 6 squared divided by 4. And just close that parenthesis, minus open parenthesis, 2 plus 2 squared divided by 4. And I'm going to close that parenthesis. So whenever we evaluate something, so we're going to evaluate our function at 6, that whole piece gets its own set of parentheses. So when we evaluate at 6, the whole thing goes in the parentheses. And then if we're going to evaluate at 2, that whole piece needs to get its own parentheses. So when you're evaluating, make sure you put it in parentheses. I don't know how many times I see students drop this, but we don't want to. Okay, so when we enter that, we get 12, which is nice. This right here is called the fundamental theorem of calculus. Fundamental theorem of calculus. If we were in class together, I would show you that I have the fundamental theorem of calculus in cross stitch, and it currently is hanging on my wall, but we are not in class together. If you want to, I can take a picture of it and put it in our Canvas class. That's pretty cool. Okay, so that is a key idea here, that the area under this curve can be found using integration. And you're probably asking, like, why would we want to? Well, we could have some really bad curves that aren't so pretty. And then it would be way easier to use the fundamental theorem of calculus. In fact, our next lesson is going to be looking at area under the curve. Okay, so I'm going to write that up formally. I didn't leave myself very much room. Okay, and so my key idea number one is my integral from a to b of f of x, of lowercase f of x, dx, is equal to my antiderivative evaluated from a to b, which is really my antiderivative evaluated at b minus my antiderivative evaluated at a. And what that is without symbols, because man, that's a lot of symbols, is the area under the curve of our original function, f of x, lowercase f of x, from a to b. Now, the rest of this lesson, we're going to be going over like little caveats, so I'm going to be adding key ideas on each of these. So this isn't the complete fundamental theorem of calculus, but it is part of it. Okay, so let's look at our next one. My papers are flying everywhere. Okay. And it says, evaluate the definite integral using the fundamental theorem of calculus and the shade in the appropriate region. So we're evaluating from -1 to 5 of 6 minus 2x. So from -1, we always go to the x-axis from our curve. And then to 5. So 5 is way down here, and so we're going to draw up to the x-axis. So note, if it's above the x-axis, we draw down to the x-axis. If it's under the x-axis, we draw up. Okay, so we're going to evaluate this. And it said shade in the appropriate region. So I'm going to shade. And shade here. Not going to stay in the lines very well. Okay, so we have that region shaded. And we have the integral from -1 to 5 of 6 minus 2x dx. So I'm just going to rewrite this because that's just what I always do. -1 to 5 of 6 minus 2x dx. Okay, I'm going to find the antiderivative. So I have 6x minus 2x squared over 2 evaluated from -1 to 5. All right, so now I'm going to plug 5 in, and then I'm going to plug -1 in. So I have 6 times 5 minus, I'm just going to type in 5 squared, because those 2's cancel, minus 6 times -1 minus -1 squared. All right, I am going to type this into the handy dandy calculator. So we have 6 times 5 minus 5 squared. Close that parenthesis. So that first piece I'm typing in is evaluating my antiderivative at 5. And now I'm going to subtract off when I'm evaluating my antiderivative at -1. So I have 6 times -1 minus -1 squared. Okay, and I'm going to close off that parenthesis. And we get 12. So my area under the curve to the x-axis is 12. Just a little sentence. Okay, so what I want you guys to do, I want you to kind of see something here, is I want you to evaluate from -1 to 3, and then from 3 to 5. And I'm breaking it up over positive above the x-axis and below the x-axis. So I'm going to integrate from -1 to 3 of 6 minus 2x dx. And I'm going to add on, so I'm just taking the different areas. The area from 3 to 5 of 6 minus 2x dx. There is a reason I'm showing you this. It's for kind of a key idea here. So when I find the antiderivative here, we get 6x minus 2x squared over 2, evaluated from -1 to 3, plus 6x minus 2x squared over 2, evaluated from 3 to 5. Okay, sorry if I keep pausing. We're having a really bad rainstorm and we're having flash floods where I'm at, and I just wanted to make sure I didn't need to go pick up my daughter. So I apologize for the random long pauses. Okay, so we're going to plug this in. And so we get 6 times 3 minus 2 times 3 squared over 2 minus 6 times -1 minus 2 times -1 squared over 2. And if you type that piece into your calculators, what you get for that piece is 16. So notice 6 times 3 minus, I'm going to cancel out the 2's, minus 3 squared, close my parentheses, minus 6 times -1 minus -1 squared, if I typed in everything correctly. 16. Well, that's higher than our area. Our area was 12. So let's see what happens when we type in this piece. So now let's evaluate the function from 5 to 3. So we have plus 6 times 5 minus 5 squared minus 6 times 3 minus 3. Oh, minus 3 squared. All right. So we have 6 times 5 minus 5 squared minus 6 times 3 minus 3 squared. We get -4. So here we get 16 minus or plus -4, which is our 12. So really what's happening, I'm going to go back up here, is if this area in purple was the purple area we just did from -1 to 2, this purple area is 16, while our blue area is -4. So the reason that is because if I was to make a triangle, our height is -4. Our width would be 2. And so if we did this old school by using geometry, we would have 1/2 base, which is 2, our height, which is -4, which gives us -4. So area under the x-axis is negative because our height is negative. So that gives me my key idea number 2. And that the area below the x-axis is negative area. So anything above the x-axis gives us positive area. Anything below the x-axis gives us negative area. What would be a wonderful test question, because this is the key idea, would be to give you a shape below the x-axis and you have to find the area of it. And it needs to be negative because it's below the x-axis. It's a great idea, Katie. Okay. So that's another part of the fundamental theorem of calculus, is area below the x-axis is negative area. Okay, so I'm going to pause the video, or you're going to pause the video, and you're going to work on example 3. So evaluate the definite integral using fundamental theorem of calculus, shade in the appropriate region. So go ahead and do this, pause the video. All right. So hopefully you were able to do this. This one's not any worse than before, but it has decimals in it, and that always makes it a little aggravating. But we do have the calculator. So that is very helpful. So we're going to evaluate the area. We're going to evaluate the definite integral using the fundamental theorem of calculus, and we're going to shade the appropriate region. So we're going to evaluate 0.125 x cubed plus 1 from -4 to 2, or we're going to find the area. We're not evaluating. Finding the area from -4 to 2. And we are going to find this area. And to keep up with my color scheme, I'll do this. And remember before, we did not have to split it up into 2 integrals, which is really nice. There are sometimes when we have to. This time we don't. And so we're just going to find the antiderivative and evaluate. So rewriting from -4 to 2, 0.125 x cubed plus 1 dx, we get 0.125 x to the 4th divided by 4 plus x evaluated from -4 to 2. Okay, so we're going to plug the 2 in, plug the -4 in, evaluate, life is good. So I'm going to plug the 2 in, and I get 0.125 2 to the 4th over 4. I'm going to make that parenthesis a little bit bigger. There we go. Plus 2 minus 0.125. I'm going to run out of room, so I'm going to bring this below, minus 0.125 -4 to the 4th over 4 plus -4. Okay. So open parenthesis, 0.125 2 to the 4th divided by 4 plus 2. So that first whole parenthesis, I'm just typing in as I see it. and then minus, open parenthesis, 0.125, open parenthesis, negative 4 to the fourth. And when you're up here, if you want to get down, you're going to press the over key. Notice that button in red right here. And that brings you back down, divided by 4 plus negative 4. Okay. And there is my second parenthesis. Feel free to pause this video as I'm typing it in. I type on the calculator pretty fast. I type on a handheld calculator even faster. But feel free to pause them as I'm going along. And just so you can see, and every button I type shows up in red on the calculator. Now I'm going to press enter, and I get that my area under the curve is negative 1.5. Okay. So my key idea here, most time people stop me right here and it's like, Katie, your area is negative. We're getting a negative 1.5 for that total area. The problem before, the negative kind of canceled out. But what does that mean? That just means that I have more area under the x-axis than I do the positive x-axis. It gives me a positional area. And so the key idea number 3 here is that the area can be negative if more area is under the x-axis. So we can have a negative area, it's just coming from below the x-axis. All right. So if you have any questions, I'm kind of moving along pretty quickly. If you have any questions, pause the video, rewatch any areas that you're stuck on, email me questions, and I can hopefully help. Okay, so before we move on, this is a lot of work. Like, this problem had decimals in it. Luckily, we had the calculator, but I want to show you something else. I'm going to go a little bit slower. If we want to evaluate this, now, if I tell you, before we do this, if I tell you on the test, evaluate using the fundamental theorem of calculus, you better write it out, all the way out. I want to see all the steps, all the gooey details. When you get to here, you can type it in your calculator. All right, so now, fundamental theorem of calculus, your calculator can do. If you hit the math key, which is my key that is highlighted in red right now, and you scroll down to number 9, it says FNINT. That's the integral or the antiderivative of a function, or it's a definite integral. So definite integral. We're going to click enter. I'm going to go through that again. So if we're back to our main screen and we want to bring up the integral, we hit math. That red key that's highlighted, it's under the green alpha key. Scroll down to number 9, and we're going to hit enter. Okay, now I'm going to type this in as I see it. The integral from negative 4 to 2 of 0.125 x cubed plus 1 dx. And I'm going to hit enter. And we get negative 1.5. We can go back to one of our previous problems. So example 2. I'm going to hit math. Scroll down to number 9. Hit enter. So the integral from negative 1 to 5 of 6 minus 2x dx equals 12. we got 12. That's kind of a handy feature. Okay, so example 4, I'm sure since I just told you this handy dandy feature, you're going to want to do it in your calculator. That's fine. I'm going to go about it a slightly different way. Sorry, I have my notes kind of scattered everywhere. Okay, so evaluate the definite integral using the fundamental theorem of calculus and shade the appropriate region. So we're going to evaluate 4 minus x squared, evaluated from -2 to 4. So -2, 1, 2, to 4, 1, 2, 3, 4. And we want to find this area. All right. So I'm sure most of you are going to go ahead and try to do this on your calculator. So I'm going to go ahead and pause and let you guys try that. Okay. And it probably didn't work. So let's look at why this isn't working. So if I integrate this, we get -2 to the 4 of 4x to the -2 dx. Finding the antiderivative, I get 4x to the -1 divided by -1, evaluated from -2 to 4. And I'm going to plug 4 in and I'm going to plug 2 in. So -4 times 4 to the -1 minus -4 times 2, -2 evaluated, let me start over, minus parenthesis, -4 times -2 to the -1. Type this in my calculator, and I get -4 times 4 to the -1, close my parenthesis, minus, open parenthesis, -4 times -2 to the -1, close parenthesis, and I'm going to hit enter, and I get -3. Okay, well, the area is above the x-axis, so this should be positive based on the graph. So notice that my graph comes up here. And when I do in my calculator, math 9, from -2 to 4, of 4x to -2 dx. My calculator freezes, it's not liking this, and this is what yours should have done earlier. And it says tolerance not met, so it's not giving me an answer. We're getting contradictory answers when we calculate this. What in the world? So the issue is that f of x, which is 4 over x squared, is not continuous. At x equals 0. So notice here that at x equals 0, we have a vertical asymptote. This line never meets, this line never meets. So we have this volcano that's going up to infinity, and that there's an infinite amount of area under here. So the area is an infinite amount. Definitely not -3 based off the picture. And so since it's not continuous at x equals 0, and x equals 0 is between x equals -2 and x equals 4, we cannot calculate the area. Okay. So my last key idea, my key idea number 4, is that the integral from a to b of f of x dx only works when f of x is continuous from our starting point to our ending point from A to B. All right, guys, this is all the problems that we are going to do today. If you have any questions at all, feel free to email me, post a message in Canvas, or post a comment on YouTube, and I will get back to you as soon as possible. Have a wonderful day.